Hello again. In this video, we're going to explore the geometric meaning of a Riemann sum when our function goes below the x-axis on our closed interval from a to b. Now, in the previous section, we talked about the geometric meaning of a Riemann sum when the function is above the x-axis on the closed interval from a to b. In that case, the geometric interpretation is that it gives us the area trapped between the function and the x-axis, starting at a and ending at b. Okay, so now we're going to look at the case when the function actually goes below the x-axis on the interval, the closed interval from a to b. How do we interpret the Riemann sum in those cases? Okay, so to explore this, let's look at example 1, part b. So the function we're going to work with here is 1 minus x squared. And we're going to try to create a left Riemann sum on the closed interval from 0 to 3 for this function. And we're going to use 6 subintervals to create our Riemann sum. Now, remember, when you create a Riemann sum, the first thing you need to do is create a regular partition of your interval, in this case from 0 to 3. Now, a regular partition means that each of the subintervals have to have the same width. Okay, and so the width of each of those subintervals is going to have to be b minus a divided by n, which we call delta x. So in this case, it's going to be 3 minus 0 divided by 6, because we're creating 6 subintervals. And that means the width of each of the subintervals is going to have to be 0.5. And then you can look at the grid points, starting at 0, which is our left endpoint. If you go up by 0.5, that'll give you all of the grid points. And of course, you need to stop at 3 because that's our right endpoint. Now, the graph of 1 minus x squared looks like this. And here's our 6 subintervals. And now we're going to create a left Riemann sum. So remember, when you create a left Riemann sum, you want to pick the left endpoint in the subinterval to determine the height of the rectangle on that subinterval. So in this case, the left endpoint for this subinterval happens to be 0. And when you plug 0 into the function, you just get 1. Okay, so this is a rectangle with a height of 1 and a width of 0.5. Okay, so 1 times 0.5, and notice here they factored the 0.5 out. Okay, the next subinterval, right here, the left endpoint is 0.5. When you plug that into this function, you get 1 minus 0.5 squared, and that's equal to 0.75, and that's the height of this rectangle. And of course, the width is 0.5, which they factored out. Okay, the next subinterval, left endpoint is 1. When you plug that into the function, you get 0. And so that's the height of this rectangle. Then the width, again, is 0.5, which they factored out. Okay, but now notice when you get to this subinterval, the left endpoint is 1.5, right? But when you plug that into the function, you actually get a negative number. You get 1 minus 1.5 squared, which happens to be negative 1.25. And that's because this is below the x-axis. And so that's what's going to happen when the function goes below the x-axis. You're going to get a negative contribution for the quote-unquote area of this rectangle. Now, it's not really the area of the rectangle, because areas have to be positive. Okay, that's why I'm calling it quote-unquote area. But it is a negative contribution in the Riemann sum. Okay, so we're going to get a negative 1.25 here for the quote-unquote height of the rectangle. And the width, again, is 0.5, which they factored out. Okay, now the next subinterval, the left endpoint is 2. When you plug 2 into the function, f of 2 is negative 3, which is this y value here. And then you multiply that by the width, which is 0.5. Again, they factored that out. Okay, and then the last subinterval, the left endpoint is 2.5. F of 2.5 is a negative number, right? It's negative 5.25. And then times the width, which is 0.5, which they factored out. So notice that each of these 3 rectangles are giving you a negative contribution in the Riemann sum because the function's below the x-axis, whereas these two rectangles over here are giving you a positive contribution. In fact, if you were to add up these two positive contributions, it would be 0.875. If you were to add up these three negative contributions, you get negative 4.75. Now, again, the area of these rectangles is not negative, right? An area cannot be negative. The area of these three rectangles is actually positive 4.75. But the Riemann sum doesn't recognize this as a positive value. The Riemann sum simply takes the y value right here, multiplies it by the width, and the y value is negative in each of these three cases. And that's why we're getting a negative number over here. Okay, so overall, the entire Riemann sum, right, the left Riemann sum for this function with 6 subintervals is going to be 0.875 minus 4.75, which is negative 3.875. Okay, and so that's our left Riemann sum for this function on the interval from 0 to 3 with 6 subintervals. Okay, so we've got to come up with our geometric interpretation for the Riemann sum in this case where the function goes below the x-axis. It's obviously not giving us an approximation for the area that's trapped between the function and the x-axis. So this is how we're going to interpret it. It's going to give us an approximation for what we're going to call the net area trapped between the function and the x-axis, starting at 0 and ending at 3. So this is going to be called net area. So what the Riemann sum is doing is it's giving us an approximation for the net area, okay, trapped between the function and the x-axis on the closed interval that we're looking at from A to B. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.